Biostat 6611, skills for the rest of your life, bootstraps and probability, it's the bread and butter, baby, what's your jam?
Greetings Bio 6611. In this set of lecture slides, we're going to work on deriving the beta coefficient formulas we saw last week for simple linear regression. We'll start with a brief review of that idea of least squares estimation, of how we're going to derive our coefficients, and then we'll get to work at actually deriving them and showing step by step how we get there. So let's start again with that review of least squares and what we're trying to do. Remember we talked about the different ways we could potentially identify the best fit line, and we ultimately came up with what we said was S equal to the sum of our residuals, or the difference between our observed value yi and our predicted value y hat I from this equation. Our goal then was to identify how we could minimize the sums of square due to error. Here we see also we can replace our yi hat with the actual fitted regression equation. The mathematical approach to doing this, we stated last time, could be done through, in our last paragraph here, specifying the sums of square error as a loss function and minimizing it over all the possible choices for beta naught and beta 1. In other words, using calculus with the first partial derivatives set equal to 0, which we'll do in the following slides. But what we're doing here is going to be the equations that demonstrate the truth of this inequality stated above, that no matter what other estimates we might come up with for beta naught 1 and beta naught, the ones over here with the hat and the star, they'll never be as efficient or as good as what we'll be deriving here for our ordinary least squares approach. So let's get to it, since we're going to walk through the math step by step. The formulas we showed previously and what we're going to demonstrate in this lecture set are as follows. And we noted last time that we can really use these to our advantage because from 5 summary statistics we can derive then or calculate the slope beta hat 1 and the estimated intercept beta hat 0. What we'll see in the following slides are these formulas derived step by step. So first we're going to solve for beta naught hat. And again, we're going to take our sums of square error, take the first order partial derivative with respect to beta naught, which we can see written out over here for our starting point for what we're going to solve. So let's pause here, switch over to a whiteboard, and work through the math step by step. Okay, we switched over to the whiteboard, so we can work through these step by step and see what we get. Obviously, the first step we have to do is actually calculate that first order partial derivative with respect to beta naught. In this case, we can think of using the chain rule from calculus, but also it'll be a bit more straightforward because beta naught we see over here is just living sort of on its own. What we see though, if we do take that first order derivative, is that we will have the sum of I equals 1 to n, where again this is our sample size of n observations in our study. It'll be negative 2 times yi minus beta naught minus beta 1 xi. Now the way we actually then identify what beta naught or beta 1 is that we'll set this partial order, first order partial derivative equal to 0, and that will essentially minimize over our sums of square error. So what we see here is then if we go to our next line, we can just rewrite this equation. We'll add another just little piece of information that's useful to note, which is our hats. Because at this point what we're now doing is setting, by setting this equal to 0 and solving, is we're actually trying to solve for that estimate of beta naught or beta 1 based on our data that again sum of I equals 1 to n. So the first thing we might want to do is to simplify this out a little bit, is we want to divide each side by negative 2. The reason we want to do this is because we can get rid of that constant term, which really isn't doing anything except making a bit of a nuisance for us. So if we do consider doing that, we'll see here we have I equals 1 to n and we just basically rewrite our equation here with our terms, and we can just note for completeness here 0 divided by -2 will still be equal to 0. Then at this stage, the useful thing that we could do at this next step would be to distribute the sum throughout our equation. So we can think of it here as being distributed out to each one of our 3 terms here. So in our next line, we have the sum of I equals 1 to n of our y's minus the sum of I equals 1 to n of our beta naught hats minus the sum of I equals 1 to n of our beta 1 hat xi. And all of this is still, of course, equal to 0 right now. Now, a few useful things we can note here that will help us simplify this even more is to consider what each one of these terms represents. Because right now, even though we haven't finished solving for it, what we have here for beta naught hat and beta 1 hat are constant values. We're solving for them, but they're going to be a single quantity based on the data we've provided. What we can't do, though, or we have to keep track of, is the fact that we have yi and xi, which both have the subscript I. So there's some unique information provided by each person, I equals 1 to n. So at this point, there's a few things we could do, but the first thing that might be most useful is to divide everything we have by n. And so I'm going to quickly erase some of our little highlights here just to make it a little easier to see that we're going to simply divide each one of our terms here by n, and because we're now introducing this to our equation, we have to do so on both sides. But what we can see here is that we have some nice things that can simplify a bit. So starting at our left-hand side here with our term y hat n, what that really becomes is the mean of the y's, because that's just the sum of our observations divided by the sample size. What we can note here then as well, we'll take a few extra steps here, but we can say first that we really have n times beta naught hat. Again, it's beta naught hat is a single constant value, so really what we're saying with the sum of I equals 1 to n is that we're just adding it to itself n times. And of course, we'll still divide it by n here. This next term over here with our beta 1 hat xi is a little trickier, but we can break it down as well. Because our beta 1 hat is a constant, we can start by just pulling that out or factoring that out here of our sum of that xi beta hat 1, and we can just have the sum of the xi's over n, all equal to n. And let's scroll down a little here to get a little more room to work with. So at this stage, we can note that we have the n's canceling out for our beta naught hat. So we have still y bar. We then still have beta naught hat just on its own. We then have beta hat 1, but what we have over here then is the mean of our x's, because we just have the sum of our x's divided by n, and that's all equal to 0. So our final step is to actually solve for beta hat naught, because again, we're trying to solve for the intercept in this case. And in this case, we can simply just add that over to the equals 0 side, and we can just say beta naught hat equals y bar minus beta hat 1 x bar, much like the equation we saw previously. However, the one tricky part that we're not quite finished with yet is the fact that we actually still have that beta 1 hat estimate in our equation. So we actually do need to finish and solve for what the slope is in order to actually get to the estimate of our beta naught hat. So let's pause and flip back over to our slides to introduce then the calculation for beta hat 1. Okay, we're ready now to follow some similar steps for deriving our intercept term, but of course we're going to have to work with it, the chain rule, a little more in detail for that first step of the partial derivative with respect to beta 1. So let's again use this as our starting point, and we'll cut over to the whiteboard to actually work through the math. Okay, we flipped over to the whiteboard. So now we see here as our starting point that sum to square error that we want to take the first order derivative with respect to beta 1. And so here we will have to apply the chain rule of calculus, and we're going to just state what we get here to speed things along, but we'll have that sum of I equals 1 to n times -2 xi yi minus beta naught minus beta 1 xi. So again, a little different because now we have our xi term here as well thanks to the chain rule. But the way we're going to solve this again for beta 1 is by setting equal to 0. And so we'll do that here on our next line of our equation. Okay, so let's set this then equal to 0 to solve for beta 1. So we see here we have as I equals 1 to n negative 2 xi times yi minus beta naught hat minus beta 1 hat xi equal to 0. The first thing we'll do that'll be useful is to divide by 2 in this case to get rid of that constant term which really isn't doing anything for us here. Another thing we can do at the same time is that we can substitute in what we just calculated for beta naught hat. Because again, we only want to solve for one unknown in our equation, and right now we technically have 2. So if we do these steps together, we see that we have the sum of I equals 1 to n negative xi times yi minus the mean of y minus beta 1 hat, the mean of x, minus beta hat 1 xi equal to 0. We then say we can do a little work to clean this up a bit for us to make it a little simpler. So we'll say the sum of I equals 1 to n negative xi yi minus y bar plus beta 1 hat x bar minus beta 1 hat xi equals to 0. So here at this point it might be helpful to actually factor in our xi term to all of these quantities. So we have the sum of I equals 1 to n negative xi yi plus xi y bar now minus beta 1 hat x bar xi plus beta 1 hat xi squared all equal to 0. With this, then our next step could be to distribute through that summation so that we actually have it going to each one of our terms separately that we can work with. So at this point what we have is, if we can get that out of the way, scroll down a little bit, we have the summation I equals 1 to n of negative xi yi plus y bar times the summation of I equals 1 to n of xi, again combining some of those steps to factor out y bar since it's a constant in this case, minus beta hat 1 x bar times the sum of I equals 1 to n xi plus beta 1 hat sum of our xi squared all equal to 0. At this point now what we can see is that we have beta 1 here for 2 different pieces, but we also then have these pieces over here which have nothing to do with beta 1. So it may be helpful in this case to actually move the pieces without the beta 1s to the right hand side of our equation, that equals 0 side, and then isolate the beta hat 1 to solve. So at this point here, if we combine these steps, we see we have beta hat 1 is equal to the sum of our xi squared minus x bar sum of xi, and that then will be equal to the sum of our xi yi minus y bar sum of our xi. Where again we can note that for each one of our summations it's from I equals 1 to n. And then technically if we just scroll down a little bit more, we can solve for a version of beta hat 1, which will be equal then to that sum I equals 1 to n xi yi minus y bar sum equals I from I equals 1 to n of xi. Divide that then by our term here, which we can just divide by right here to have that sum xi squared minus x bar sum of xi. Now, the one caveat if we were to stop here is that this is just not super nice to work with. It has a lot of terms that we maybe wouldn't think of as the difference between the mean and the observation, or different types of summary statistics. And so what we can do is we can work to actually show that this is going to be equal to what we have in our notes, or what we presented previously, which is that I equals 1 to n xi minus x bar, yi minus y bar, and then all of that divided by the sum of our xi minus x bar squared. Now, of course, this doesn't look very intuitive, so we're going to spend a minute walking through working backwards from these to see if we can actually get our equation here to match and also here to match for both our numerator and our denominator. So let's pause here for a second and get a clean whiteboard to work with. Okay, let's start with working the numerator here to see what we can get if it looks a little cleaner if we work backwards. So we can start here with that sum xi minus x bar, yi minus y bar. The first thing we can do is multiply our terms together. So we have something like the sum of our xi, yi, then maybe something to kind of looking forward to what we're trying to solve at. Maybe we'd put next our y bar minus xi minus x bar times yi. And then we see we have as well plus x bar, y bar. We can then distribute our summation throughout. So we have the sum of xi, yi minus the sum of y bar xi minus the sum of x bar yi plus the sum of x bar y bar. So a lot of distributing our terms here. We can notice a few things right now. First is that what we have here is actually already what we want for our equation. And in fact, also what we're trying to show as well here is equal to what we have above. We just need to rearrange it slightly. So we see here we have the sum of our xi, yi minus y bar, the sum of our xi. So what we're really left having to do is demonstrate that our terms over here can be shown to be equal to each other. And so what we can see here is that we really have minus x bar, the sum of yi, plus n times x bar, y bar. And just briefly noting here that at this point here, because x bar and y bar are both constants, we can just count how many times we take that summation, n times. And here we just factored out our x bar, under taking into account that it also is a constant. The next little trick we can do here is that we can multiply in our term here. Maybe we'll highlight it just to make it a little more apparent. We can multiply each part n by n over n. So that's really multiplying by 1. And when we do this, what we see here is that if we take into account our y bar divided by n, we have the mean of n, actually the mean of y. And so at that point we would have n x bar y bar plus our x bar y bar from above. And we see then that this term here will be equal to 0. So what we are left with here is that equation we solved for previously for our numerator. So we can demonstrate that that holds. Let's take a quick look at the denominator. And I'll scroll down and get us some more whiteboard space to work with. So in this case, we want to focus a little more on that denominator. And so here, working backwards, we have something a little maybe different or trickier to work with, but what we had above there in our nicer format is the sum of xi minus x bar squared. So again, we can actually square this term and see what we get. And we have that sum I equals 1 to n. We would have xi squared minus 2 x bar xi plus x bar squared. And at this point, we can again distribute our summation throughout these additive terms. And so what we really have is the sum of our xi squared minus the sum of 2x bar xi plus the sum of x bar squared. Again, we can note that with our constant terms, we can do a little simplifying magic here, where we still have that sum of xi squared. We can put minus 2x bar, sum of xi, plus n times x bar squared. So what we can note at this stage is that what we do have here is that term, that sum of xi squared, that we want in our solution to beta hat 1 through our solving of that first order partial derivative, but we're still missing that minus x bar sum of xi. Because right now what we have is 2 times x bar sum of xi. And so what we can do in the next step is we can separate those out, so we have minus x bar sum of xi twice, just literally writing it out, plus n x bar squared. The reason this is nice is that now we see here we actually do have the component that we derived through our solving of beta hat 1, and what we have to do here now is show that this can be equal to 0 to finish the steps. So we'll scroll down a little here to give us a little more room, and we'll just focus on showing that that's equal to 0. And so we can note here, again, is very similar to before. We have our negative x bar sum of xi plus n x bar squared. What we can do is we can multiply by 1 that n over n x bar sum of xi plus n times x bar squared. And again, this is a nifty trick here, because we can multiply by these terms as we've done before in some other equations in class, but because it's at this point multiplying by 1, we don't have to do this to any other part of our equation. But what we can note here is, again, if I could write these in a little more straightforward way, is that we have the sum of xi divided by n. So what we really have then is n times x bar plus n times x bar squared, which then gets us to negative x bar squared plus that positive x bar squared, which helps us to show that this does in fact go to 0, and therefore we've demonstrated that equation for beta hat 1. And so that concludes this lecture of deriving our terms and trying to manipulate the algebra in ways that make it hopefully a little nicer to work with. But we'll also do some work with deriving the terms for our variance and applying some of those properties in the next lecture set, as well as looking at the relationship between the coefficient of determination r squared and our correlation coefficient r.